Hello, students. Today, our topic is amorphous polymers. In this lesson, we will give a brief overview of the concept, types, and applications of amorphous polymers. First, concept of amorphous polymers. The aggregated state of polymers refers to the geometric arrangement between macromolecules. The aggregated state structure includes crystalline state, amorphous state, liquid crystalline state, oriented state, and other structures, which are formed during the molding process. The chain structure of polymers is the main factor determining their basic properties. The aggregated state structure directly determines the properties of the polymer and its products. Amorphous polymers in the aggregated state are also called non-crystalline polymers. They are polymers in which the molecular chains lack long-range ordered structures in the solid state. When cooled, these polymers do not form a regular lattice structure. As a result, they exhibit unique physical and mechanical properties. From a molecular structure perspective, amorphous polymers include the following types. Polymers with poor chain structure regularity, such as PS, polystyrene. Polymers with some regularity in chain structure, but with extremely slow crystallization rates, such as PC, polycarbonate. Polymers that are in a highly elastic state at room temperature and are difficult to crystallize, such as general rubber materials, for example, PB, polybutadiene, as well as the amorphous region of crystalline polymers. Second, amorphous polymer morphology. When applying amorphous polymers, the mechanical morphology of the amorphous polymer should be analyzed through the temperature deformation curve. A constant external force is applied to a sample of the amorphous polymer, and the relationship between the deformation and temperature during a constant rate heating process is observed. This gives the temperature deformation curve for the polymer sample, as shown in the diagram below. From the diagram, it can be seen that the typical temperature deformation curve of an amorphous polymer has two regions of sharp slope change. These two transition regions divide the temperature deformation curve into three regions. Each corresponds to a different mechanical state. In region 1, the temperature is low. The chain segments are still in a frozen state. The polymer deforms little under the applied external force. It exhibits Hookean elastic behavior. When the external force is removed, the deformation immediately recovers. This results in a material that is hard and brittle in performance. This mechanical state is similar to that of inorganic glass. This state is called the glassy state. As the temperature increases, the chain segments can move. The deformation gradually increases, entering region 2. At this point, even under small external forces, a large deformation can rapidly occur. And when the external force is removed, the deformation can gradually recover. The property by which a material undergoes large deformation under an applied force and returns to its original shape after the force is removed is called high elasticity. The corresponding mechanical state is called the rubbery state. When the temperature reaches high enough, the large macromolecules undergo relative displacement, entering region 3. The polymer completely becomes a viscous fluid. The deformation is irreversible. This mechanical state is called the viscous flow state. The region where the transition from the glassy state to the rubbery state occurs is called the glass transition region. The temperature at which this transition occurs is called the glass transition temperature. It is denoted as Tg. The temperature at which the rubbery state starts to transition to the viscous flow state is called the viscous flow temperature. It is denoted as Tf. The deformation transition region between these states is called the viscoelastic transition region. The glassy state, rubbery state, and viscous flow state are known as the three mechanical states of polymers. Analyzing the mechanical morphology of amorphous polymers has the following practical significance. First, it can be used to guide the molding and processing of polymer materials. The molding process of polymers is essentially a process of mutual transformation of polymer mechanical states. Molding is generally carried out in the viscous flow state. The molding temperature range is higher than the viscous flow temperature, but lower than the decomposition temperature. Second, it can guide the appropriate use of high polymers. When the glass transition temperature Tg of a material is higher than room temperature, the material is used as plastic or fiber. The higher the glass transition temperature, the better the material's heat resistance. When the glass transition temperature is lower than room temperature, the material is used as rubber. Moreover, the lower the Tg, the better the material's cold resistance. When the viscous flow temperature of a material is lower than room temperature, such materials are used as adhesives or coatings. In summary, amorphous polymers, also known as non-crystalline polymers, have several types based on their mechanical morphology, including the glassy state, rubbery state, and viscous flow state. At room temperature, glassy state materials are used as plastics and fibers. Rubbery state materials are used as rubber. Polymer molding is essentially the mutual transformation of polymer mechanical states. Molding is generally carried out in the viscous flow state. The molding processing temperature range is greater than the viscous flow temperature, but less than the decomposition temperature.